Alright, today I'm going to show you how you can fit a one-segment shifted geometric model very easily in Excel. So the data that I'm going to consider is the data set that we used in class. This is just the hypothetical Dollar Shave Club data set. But in general, what we need is we need one column that represents kind of our unit of time, and the other column represents as we move forward in subsequent months after a particular cohort has been acquired, the number of customers from within that cohort that are still with the firm. So month 0, this should represent the number of customers that were originally acquired. And then in all these subsequent months, this is the number of customers that were alive in that month. Obviously, if you had a data set where the unit of time was weeks or days, there would be no issue applying the same model instead to that. So what we're going to do is we're going to take this data and we're going to port it over to this tab over here. So I just kind of copied and pasted it. And the first thing that we're going to get is what the percent of the cohort that's still alive in subsequent months is. So this is saying that 39.4% of the customers 12 months after they've been acquired are still with the firm. The next thing that we want to get is what our model-based expectation is of the percent of the cohort that's still alive in those months. And then finally, we want to be able to find the best fit. We want to compare what we expect to what we actually observe. And so what this column F represents is the difference between what we expect the percent of the cohort that's alive to be to the actual percent of the cohort that's alive. And we're going to square that so that all the values are positive. And then what we want to do is we want to get a measure of error and make that error as small as possible. Now in this particular circumstance, we want to train our model on some of the data and see how well it predicts the rest of the data. So for our purposes, what I'm going to do is I'm going to assume that we don't get to see any of the data in months 8 through 12. I'm going to assume that we only see the data in months 1 through 7. So what I'm going to do is I'm just going to remove all that data. I'm going to define the sum of the squared error to be my error, kind of the difference between expected and actual squared summed over the first 7 months of the data. And that's what this represents. Now, these figures represent kind of the percent of the cohort that I expect to be alive in subsequent months, assuming that theta, which is the probability of churn, is 50%. So obviously, if the probability of churn is 50%, then in month 1, I'd expect that 50% of customers are alive. In month 2, I'd expect that 0.5 squared, or 25% of the customers, will still be alive, and so on and so forth. Obviously, if this figure was 0, then I would expect that no customers would ever churn. And if theta was equal to 1, then I'd expect that every customer would churn in the first month. Obviously, the truth is going to be somewhere in the middle between those two. And the way that we find out what that somewhere in the middle is by using solver. So essentially, what solver allows us to do is make the sum of the squared error as small as possible. So I'm setting the objective to a minimum by changing the value of theta. And the only other things I need to do are I need to take into account the fact that, because essentially we're assuming this kind of coin flipping model, that there's some probability of churn, and every month you kind of flip your coin until that coin comes up heads. We know that that coin must have a probability that's between 0 and 1. So essentially these constraints impose the fact that theta must be between 0 and 1. So we just kind of keep everything else as it is. We run solver, and there we go. This is basically saying that when the per period probability of churn is 11.2%, the sum of the squared error is 0.9%. That seems pretty small. So the next question is, how well does that actually fit the data in the holdout period and in sample? And the way that we can do that is by kind of going back to this data set, giving ourselves back months 8 through 12, getting the observed percent of the cohort that's alive, and comparing it to what our model-based expectation is under this 11.2% per period probability of churn, and I just kind of gave you the answer down over here. We see that kind of the expected percent of the cohort that's alive just drops off really, really quickly. We're essentially kind of assuming a much more pessimistic view of what the cohort evolution retention is going to be. And that is exactly as we'd expect, given what we've talked about in the class so far. So obviously, this is a particular example using that contrived data set, but again, if you had a different data set, or if you had the same data set, but you wanted to see how well the model fit over a different number of calibration periods, again, the only thing you need to do is essentially change this squared error sum to some other number of months, do solver on that, and then see how you did. So hopefully this is a helpful explanation, and you can use this when you run your next retention model. Although hopefully you'll very quickly move to something better than this. Thanks.